All right, so after today, you should be able to explain the concepts of evaporation, condensation, and vapor pressure. And also, you should be able to identify all the different parts of a phase diagram. Evaporation. What do you call the process by which a liquid becomes a gas below boiling point?
Evaporation.
Evaporation. Okay? Who can explain what exactly happens when a liquid molecule evaporates? The key thing is to remember my analogy. We're all tied together by ropes.
Oh, wait, never mind.
You are now a liquid, so you're roaming down the hallways, flowing past each other, but still interconnected with each other. What happens when they evaporate? At boiling point? Below boiling point. It would be like me coming up to you down the hallway somewhere and giving you the slip. Somebody from attendance is checking you out, so I cut you loose. Okay? It's where you have molecules usually near the surface, that come in contact with an extraordinary amount of energy, and they individually have enough energy to break the hydrogen bonds and become gas. The only other way is through boiling. And boiling, you heat them up from the bottom, and slowly the water near the bottom gets hotter and transfers energy to the top, closer to the middle, then finally to the top, until everyone gets to be at 100. And at that point, they start boiling throughout. Why is evaporation the key to life here on Earth?
The water cycle.
Okay, so why is that important?
Because it puts water and stuff around everywhere. I'm saying.
Because if water doesn't evaporate, then we couldn't get water in places where there weren't oceans. Boom.
Well, I don't know.
Okay, so Mars is almost twice as far away from the sun as the Earth is, and yet the sun's heat hits it with such ferocity that if you had a mask on, because obviously there's very little oxygen in the Martian atmosphere. They still have an atmosphere, but there's very little oxygen in the atmosphere. If you were to have a mask on so that you could breathe, and you were to step outside, the water in your skin, in your tissue, would boil away.
Ain't no atmosphere.
Okay, I just said it does have an atmosphere, but it gets so hot during the day that it would boil away. You would roast alive. Simon, but it is why aren't we roasting alive, since we are 2 times closer to the sun? Yes. The water vapor in the atmosphere. Not only that, but the liquid water in our oceans. The water, we have so much water on our earth that the water is able to absorb the blasting heat from the sun and circulate it in what we call the water cycle. Okay? Perfect example. Who's ever lived out west? West, where? Arizona. Okay, perfect. Do you remember moving to East Tennessee?
I thought I was drowning.
Okay, why?
Because there's so much water in there. It's just so awkward.
Yes. So, actually, the people here in this classroom that are closest to understanding what it would be like to live in Mars is Phoebe. She lived out west. Where did you live?
California.
Okay. She probably, unless, where? In Baja? No, okay, no. All right. So you understand what it's like to live, because she lived in an environment where there was very little moisture in the air. During the day, how hot would it get?
The hottest was like 109.
And at night, how cold would it get?
Very, I have no idea, but very.
Okay, they would need air conditioning during the day. They would shut off the air conditioning in the late afternoon, and they would put their heating system on at night. You go camping, you would strip during the day. Actually, you would have to be very careful you don't strip all the way, because you sweat, but that perspiration leaves your body so quickly that you don't feel like you were sweating. What was the first summer like here for you?
It was just weird. Very, very wet.
Okay, so this is what Phoebe experienced. She would go out in the sun and it would be blazing hot. She would find a tree, which were rare things. She would find a tree or anywhere where there was a shade, and she would sit in the shade, and then all of a sudden the temperature would drop 20 degrees, 30 degrees, and it would be comfortable under the shade. Then she came over here where it was blazing hot, middle of summer, so she got under a tree for shade, and what did she discover?
Still hot.
It was still hot. Okay, there are in Arizona, there's one source of heat, and that is from the sun. Here in East Tennessee, what she did not realize is that there were two sources of heat: the sun and moisture. Okay, so what would happen? Think about it. If there is moisture in the air, this water droplet, this water molecule that's in the air right here, what is its temperature?
Room temperature.
No. Room temperature is probably 74 on the average. That means that these water molecules are hotter, there are things that are cooler, and there's probably things that are somewhere in between. How hot? If this is a gaseous water molecule, probably not 100, because 100, it's right at the border, can be liquid or gas. It's probably above 100. Okay? So this water molecule that's in the air right here is over 100. Let's say it's 110. Phoebe's forehead is probably 35, 36. If the core of her body's 37, her forehead is probably at the surface 35, 34, 33. Okay? 110, 33. What happened when that molecule hit her forehead?
Yeah.
Transfer of energy. From where to where? From her forehead to the water. Her forehead is 37. So she could not escape the heat. The heat that water absorbed from the sun came after her. And literally, one of the reasons why we feel so hot here in the summer, these football players out there, is you have millions and millions of water molecules condensing on your skin, giving you their heat. They're cooling off and you're warming up, which causes you to perspire even more. No, that's what we call, when a Coke can has condensation, we call that sweat. It's not really sweat. Sweating is what you do when all that heat starts getting on your skin. So, how does evaporation preserve human life?
It keeps it moist.
So, Phoebe's getting too hot. She's climbing up there, 37, 38, 39, 40 degrees Celsius. How does her body deal?
It evaporates.
Okay, so now you've got water on the surface of your skin. In order for the water to evaporate, what does it have to do to the heat in your body? Take it away. It absorbs the heat from your body and takes it away. Now, our problem here in East Tennessee, Mortal's problem, Ryan's problem, is that there's already so much moisture in the air that it's very difficult for the water to evaporate off our skin. Now, Phoebe learned to always take a bottle of water everywhere she went. She was constantly hydrating herself. Why? Because there she would never feel herself sweating, because as soon as those water drops emerge from her sweat gland, the water would evaporate. There's so little moisture in the air that would automatically evaporate. So she can become very dehydrated very quickly without ever feeling like she has sweated. Here, all of a sudden, she was doing the same activities and she felt drenched in sweat because there's so much moisture already in the atmosphere that it took a long time for it to evaporate. Okay? That's how important it is. So what is condensation? Condensation is that gas molecule finding her forehead and finding that her forehead is frigid and actually condensing, going back into liquid phase, giving her heat. In South Florida, we didn't have, when I was growing up, we didn't have a central heat and air. Okay, we had windows. That was it. So I would be, in the middle of summer, I would take a shower. And the process of toweling myself dry, I would start sweating. I wasn't sweating. It was condensing on me. So I would wipe my face, and as I started through the rest of my body, by the time I got down to my legs, I had to wipe my face of condensation. It wasn't sweat, it was condensation. It was so humid that it was condensing on my skin. All right, question.
Sticking to a bigger piece this time.
What's that?
Carbon dioxide.
Water vapor.
Most people say carbon dioxide.
It's just carbon.
It is wrong.
Carbon.
Carbon dioxide cannot be seen.
It's carbon.
Carbon dioxide cannot be seen. I'm breathing out slightly more carbon dioxide, can't see it. But during it, when it's cold outside, you do breathe something out that can be seen. Water vapor. What you're seeing is little drops of water that have condensed when it met up with the carbon dioxide. The carbon dioxide is going to be around negative 78 degrees. This is hot water. Okay? So hot water is going to have a lot of evaporated water near its surface. So what happened when the evaporated water met up with the carbon dioxide? Who gave energy to who?
The water gave energy to the ice.
Whoever is hotter gives energy. So when the water gave energy to the carbon dioxide, its temperature went below boiling point and it condensed.
So it's ice?
No, it's dry. If you could see it, there would be globules of water that are light enough to be suspended in the air. Okay, Phoebe and Natalie, I would have. Let's see, who was the one who was doing the cauldron? It was one of the police. Who was?
Police.
I don't know. He's the one who did the cauldron for us, and I asked him to. He had to get hot water, so he had to go to the shower and actually get hot water. It would work with cold water, but it wouldn't make as much vapor. Why would it not make as much vapor? The cold water would have some evaporated molecules, but not as much. The hotter the water, the more evaporated molecules. What I wanted you guys to see in the audience was the evaporated molecules that had recondensed. So he would throw, right before we would start the show, he would throw a block of carbon dioxide in that cauldron, okay, with hot water, and what you were seeing was the recondensed water vapor.
Yep, lots of bubbles coming up. And one thing you may...
But most people would say that, ooh, that's carbon dioxide. No, it's water vapor. Okay. I'm going to draw a phase diagram. You would be wise to draw it along with me.
What's a phase diagram?
You're about to see. y-axis, x-axis.
Wait, is that already drawn on here?
That's an example. I would draw this one.
Alright.
On the y-axis, we're going to have pressure. Put pressure on the y-axis. On the x-axis, temperature. We're going to have 1 point on the y-axis. So about halfway up, that's going to be 1 atmosphere. That is the pressure at sea level. And I want you to make a dashed line across the graph all the way to the other end, symbolizing where 1 atmosphere is. Okay? 2 points. 100 and 0 degrees Celsius. 100 and 0 degrees Celsius. And right below 0 is a 3rd point. Okay? Draw dashes going up. Then I want to point like that, a little bit, just a little bit beyond 0 degrees. And then I want you to take that point and intersect where the lines intersect. And then go to the origin. This is going to be A, B, C, D, E, and F.
What is it called?
Which one? This one? This is where that point is. Okay. If you go to Cumberland Gap State Park, you find something very interesting if you hike up to this high point. Has anyone ever gone to Cumberland Gap State Park? What do you find up on that hike? On the top of that hike? Hush. Esther, do you remember? What? Remember seeing a disc up on this that looked like this? Do you remember what that was? You could put your foot right where that intersects.
How many different states?
That's 3 states. At that point, that is the point at which Tennessee, Kentucky, and Virginia intersect.
I've been to Four Corners, same thing.
Same thing. Okay. This is called, letter B is called triple point. What phase is on the left side of this graph? The frozen phase. What do we call frozen phase? What do we call the phase that is middle temperature? What do we call the phase that is high temperature? Guess what letter B is? Triple point. It is the temperature at which all 3 phases of matter can exist.
Wait, isn't there also places like up north where the pressure's so high?
No. Okay, where is boiling point? No. Where is boiling point? Letter C is incorrect. Letter C is called normal boiling point. Normal boiling point is the temperature at 1 atmosphere of pressure where a liquid turns into a gas. But what's the key? for that, Phoebe. 1 atmosphere. Okay, Marie was talking about, can't you go up north where the pressure is... No, actually, for the most part, the pressure decreases as you go up north because the elevation gets higher. We're about 700, 800 feet above sea level here. At sea level, Miami Beach, you have close to normal boiling point.
Places in the North Pole where the water pressure underwater is so great, the water.
Maybe. Yeah. Okay, so where is boiling point? No. What? No.
B to F.
What?
B to F.
B to F is boiling point. Why?
How did I cheat?
What?
Depending on where you are.
Depending, okay. If you go to Oak Ridge, Tennessee, your boiling point is not at 100. It's around 99.3, 99.4, depending on the air pressure that day. Why?
Because we're up higher than down, yeah.
If you go to Pikes to Colorado Springs, the temperature may be 92. Why? 7,000 feet above sea level. Let's cut it out. If you take the train from Colorado Springs all the way to Pikes Peak, you're at 14,000 feet above sea level, and you will boil around 88.
Wait, so what about like at the top of the river?
It would be somewhere below that. Okay? That's why you have to have different cooking temperatures for different altitudes. Because boiling point changes with pressure. What about Death Valley?
You have to heat it up more.
Higher. Why? Below sea level. Below sea level. Where is melting point? Where's melting point? B to E. This whole line is melting point. What is D? Normal melting point. What is normal melting point? At 1 atmosphere. Water will freeze in Miami. Water would freeze at 0. Miami Beach, water would freeze at 0. But here, it's going to freeze a little bit below or a little bit above? A little bit below, because our atmospheric pressure is slightly less than 1 atmosphere. A little bit below. Folks, it's all dependent on air pressure. What's letter F? This is called critical temperature. Draw a line straight up. Beyond critical temperature, it doesn't matter how much pressure you put on it, it is not ever going to liquefy. It will remain a gas. Beyond this point, it's a gas all the way up. Why? Because these molecules have so much energy that they can't possibly ever connect with another molecule. All right, so let's look at these phase changes.
Well, then what is E? Is that where it...
E is called critical pressure. Beyond that point, the pressure is so high that it can't liquefy.
Okay.
All right, so solid to liquid, what are we going to call it?
Melt.
Liquefaction. Or, I think it's, you can call it melting, liquefaction. What about liquid to solid?
Solidification.
Actually, it's called solidification, or it's called crystallization. How about solid to gas? Sublimation. How about gas to solid? Deposition.
Wait, so
Solid to gas is sublimation. Carbon dioxide sublimates.
Can they make things go to like a solid, like in a reaction?
You would have to decrease the pressure, yes.
We should do a demo of that.
How about liquid to gas? Evaporation or vaporization
Subliminal what?
or boiling? How about gas to liquid? Condensation.
What does it say in the bottom?
Sublimation. Now, this is actually a very, very weird phase diagram. 99.999999% of all the molecules don't look like this. Their phase diagram does not look like this. Let me show you why. Go to triple point. Leave the temperature the same, but increase the pressure. So you're going up. Okay? You're increasing the pressure, so you go up. What phase does it go into? That arrow is pointing you to the most dense phase. Water. Water's most dense phase is liquid. Think about it. You're at the point where all three phases of matter exist. What happens if you put pressure on them? They're going to have to go to whatever phase takes up the least amount of space. In this case, it's liquid. Okay, now contrast that with carbon dioxide. Let's draw another one. What is melting point? No, let me change that. What is condensation point?
F.
No. D to A. Why? Well, first of all, condensation point is the same thing as we usually know it as boiling point. It's the whole line. It all depends on atmospheric pressure. What is normal condensation point? F. Now that is F. What is normal freezing point? Nope. Nope. E. Right there, where one atmosphere intersects, is normal freezing point. What is critical temperature? The temperature above which it doesn't matter what pressure you put it on, it's always going to be a gas. Right there. What is deposition point? No. Deposition point. That's right. That's deposition point or sublimation point. What is triple point? You want to see triple point? This is kind of cool, but you'll have to be patient. It's about a 7-minute video, so we have barely enough time.
You know, as you look in chemistry, there are many aspects of chemistry where it's important to study, and you look at the atmosphere, and one of the major components of atmosphere is nitrogen gas. Well, nitrogen gas can exist in many other states, and so we're going to look at some activities involving nitrogen gas in the liquid state. So, what we're going to do is get some liquid nitrogen. Now, liquid nitrogen is a substance that is approximately 190-some degrees below 0 Celsius. We have it inside a Dewar flask, a specially prepared flask that has a thermos lining that will keep it cool for a while. And so what we're going to do is pour some liquid nitrogen into this little plastic cup. Now we're going to pour it in and just keep pouring in, and we want to get the cup cold, colder, colder. I think that's good enough.
You're a cool teacher, Mr. Hepburn.
Oh, thank you. So that's by itself could offer a lot of demonstrations. But what we're going to do is we're going to reduce the pressure by using a vacuum pump. We're putting this bell jar on top, and what we're going to do is turn on the vacuum pump, and what that's going to do is reduce the pressure. And so if we could have the camera just watching what's happening.
Okay, so some of those nitrogen molecules are boiling away. Are they the fast-moving ones or the slow-moving ones? So what's happening as they go away, what's happening to the temperature of what's left? It's going down. So this is kind of neat. By reducing the pressure, you're increasing the boiling. By increasing the boiling, you're decreasing the temperature.
Over here.
Right. You have to keep adding heat to boil water.
Of course, with liquid nitrogen having a boiling point so low, you can see that it's boiling.
It was just about ready to hit triple point there, but then a bunch of it boiled away. Getting closer. No, you have to.
What I ask my students to think about is what's leaving, the faster moving particles with the most energy or the slower moving particles. As the fast moving particles are leaving, it leaves behind some of the slower moving particles that have a little less average kinetic energy. What we're doing is we're getting down close to that triple point. And
there. Liquid, solid, and what you can't, it's harder to see, are little bubbles going up. All three phases of mass.
See that?
we are now at the triple point.
Okay, pressure built up because the gases couldn't escape. Pressure built up and blew away the solid layer, and then of course everything had to go back to
Of nitrogen.
And what you were seeing is actual solid nitrogen. Now,
And what happened with that?
well,
I didn't notice what happened.
it did form the solid. Were you able to get this?
Let me show you what's going on. Okay, so we are here, it was boiling there. But as it boiled, the hotter molecules left it and it started cooling it off. Cooling it off. And they're taking away the energy. So you're moving left and down, and there is the triple point.
Okay, let's just quickly, while we're letting this go, do you want to go over to the graph and talk about it, Mike?
Go ahead.
Oh, okay. Recognize that liquids have various boiling points. It depends on what particular atmospheric pressure that liquid is at. Water normally boils at 100 degrees Celsius if you're at 1 atmosphere. Now, if it's starting to go again, Mike, let me know.
It is gone, and what we've done is, what we've done is we are at that equilibrium point where it's really now oscillating back and forth
Okay,
between the solid.
what happens is vapor pressure is the pressure that the gases can exert. It's kind of like part of atmospheric pressure. So when it erupted like that, what happened to the pressure inside the container?
It went away.
No. It's the container's trying to suck it away, but when all that gas erupted, now that gas, which was down here, has become part of the air. It switched sides. So you increase the air pressure. When that blew up, it increased the pressure, so it knocked everything back up.
But doesn't
So
the
it had to
pressure
go
in the
back
cup-
down. What?
But doesn't the pressure in the cup, like, decrease?
They're sucking the air out. But at that point, when so much air came out, then the pressure went back up, and then the machine had to suck it back out. Yes?
Is there a way to prevent it from?
And the liquid states. And I've actually had this happen where it will actually, you can tell how many oscillations it's gone to, and it does something different each time I do it. It will actually pancake out of there. You'll have a layer, and then
Yes, as you leave, turn in 12.4. It needs to be turned into the box.
a liquid
What? I don't think so.
and a layer of liquid, and it will actually start keeping those layers and pushing them up out of the bowl.
You would have to decrease the pressure and decrease the temperature at the same time. They're not decreasing they're letting it naturally decrease.
There's your solid nitrogen, and we were right at that triple point.
There.
Excuse me, Jeff.
Okay, so now the gas phase still exists, so it's trying to get out, so it has to blow up through the solid phase in order to get out. Yes?
They could like make it so that it like after it froze, if they like somehow loosened the pressure under it and then they took that vacuum thing off, could they would it like sublimate immediately or?
Yes.
Wait, but what happens to the solid phase after it goes out of the cup?
After it goes, it becomes part of the atmosphere, so the atmospheric pressure goes back up.
And so, as I was saying, water normally boils at 100 degrees Celsius. That's when you have an atmospheric pressure of 1 atmosphere. What happens if you take water up to Leadville, Colorado, where you're about 10,000 feet? Guess what? At the higher atmosphere, it reaches its boiling point at a lower temperature, and water will boil at 9